x over y, and this is equal to x squared y cubed plus 1. Okay, now this logarithmic differentiation shows us what we call implicit differentiation. So this is implicit differentiation. Okay, repeat that word. Now what that means is sometimes it is not possible to make y the subject of the formula, and when it is not possible to make y the subject of the formula, what you can do is just differentiate both sides, keeping in mind that y is a function of x, and then whenever you're differentiating y, remember that it's a function of x, then you need to add dy dx. Now this one here, it's possible to make y the subject, or not make y the subject of the formula. It's still a little bit tricky, but we can simplify it so that our derivative is easier to calculate. So how we do this, we can multiply by y throughout. So I have x is equal to x squared y cubed plus y. Now here, making y the subject of the formula is quite tricky, like I said, because you can factor y out, but you'll still have y squared there. So what you do is you just go ahead and differentiate both sides, and then you'll collect all your y primes on one side and make that the subject of the formula. So here, when I differentiate the left-hand side with respect to x, I get 1, and the derivative of this one here, I must use the product rule. The reason I use the product rule is because this is a function of x and y is also a function of x. So I have two functions of x that I'm multiplying. So the first function, let me just make space. So the first function is x squared, so its derivative is 2x, and then y cubed should remain as it is. And then the second one, the second part of the product rule, the x squared must remain as it is, and then I must differentiate y to the power of 3. So differentiating y to the power of 3, I get 3y squared, that's on the outside. Then I go inside to differentiate y with respect to x. When I differentiate y with respect to x, I get y prime, okay? And then the derivative of y, this is just y prime. There's a prime over there. Okay, and then what I do is I collect my terms with y prime on one side and then make y prime the subject of the formula. So to simplify, first of all, I have 2xy cubed, and then I have 3 x squared y prime plus y prime. So here I will factor out y prime, so I have y prime 3x squared y squared plus 1, and then this 2xy cubed, I can subtract it so it's on the other side with 1. So this is equal to 1 minus 2xy cubed. And then I divide by this on both sides because I am only interested in y prime. So I will have y prime, and this is equal to 1 minus 2xy cubed divided by 3x squared y squared plus 1. Okay, I think I did not do this. What did I write? Okay, let's see. So this should be a 4. Let's just correct that. And then This should be a 4. That's a 3. Okay, sorry. What do I have here? This is a 4. And the 4 comes down. I'm left with the 3. So this should be a 4. And that's a 3. Okay, I think now it's fine. So 4x squared y cubed plus 1. Okay, so that's basically how we would do it. So if it is not possible to make y the subject of the formula, what you do, just go ahead and differentiate on both sides. And then remember, when you're differentiating y, after you've differentiated the outside of y, on the inside of y, you must have y prime or dy dx. And the derivative of that should be equal to y prime. So this is called implicit differentiation. So logarithmic differentiation is an example of implicit differentiation. Let's look at some of the exercises. This is exercise 12.10. We have x squared plus y squared. This is equal to 2x plus y. So here again, this one you can make y the subject of the formula by completing the square, but that seems very complicated compared to just using implicit differentiation. So implicit differentiation is best. What you do, you just differentiate both sides and then you'll collect y prime as the subject on one side. When I differentiate x squared, I get 2x, and this one I get 2y, and then y prime, and then I get 2 plus y prime. And then I'm going to collect all my terms with y prime on one side. So I have 2y y prime minus y prime. This is equal to 2 minus 2x. Then you factorize y prime out. So this is y prime, 2y minus 1. This is equal to 2 minus 2x. I have y prime. This is equal to 2 minus 2x. This is divided by 2y minus 1. Okay, so we've made y prime the subject of the formula. Now instead of y prime, you can also write dy dx. That is perfectly fine. We have y over x minus xy minus 1. And this is equal to 0. This one, it's very easy to make y the subject of the formula, because with the first two terms you can just factor it out. Then to do that, we have y 1 over x minus x, and this is equal to 1. Okay, so I took the 1 to the other side, and then I will divide by this bracket. But before that, I can always combine these two fractions together. So I have y, and then I will have 1 minus x squared over x, and this is equal to 1. So the denominators, I need to make them the same. So when I change this fraction to have a denominator that is equal to x, in the numerator I end up with x squared. Then making y the subject, I have y is equal to x over 1 minus x squared. Then to work this out, I just use the quotient rule. So the quotient rule says my denominator must stay the way it is. Then the derivative of the numerator minus the derivative of the denominator, and then the numerator must stay the way that it is. And then I divide this by 1 minus x squared. So that is just the quotient rule. Then what I have, this is 1 minus x squared plus 2x squared, 1 minus x squared. Now in the numerator, I can multiply out the bracket and simplify this. This is just 1 minus 2x plus x squared plus 2x squared. I need to get this squared. Sorry, that is not correct. This squared there is not correct. This one here, this should not be squared. If you look at our formula, it should just be, the squared is not outside the bracket, but it is inside the bracket with the x. So it's 1 minus that. Okay. Like that. So that is the way it's supposed to be. And then what I have is 1 minus x squared plus 2x squared over 1 minus x squared. And then this is equal to 1 plus x squared over 1 minus x squared. Okay, so that is how we would work that one out. And then we can look at one more. If I have y is equal to e to the power of sine x, this is equal to x e to the power of cos y. Okay, so again here, making y the subject of the formula is pretty difficult. So just go ahead and differentiate both sides and then make y prime the subject. So remember, when you have something like this, you must use the product rule, because y is a function of x. So I will start with the first one as it is. So y, and then the derivative of e to the power of sine x. So first it stays as it is, and then I multiply by the derivative of sine x, which is cos x. Then I add the derivative of y, which is just y prime, and then e to the power of sine x stays as it is. So that's the first one, plus that's equal to. Then on the other side, x will stay as it is, and then e to the power of cos x first will stay as it is, and then you multiply by the derivative of cos y, which is sine y, and then the derivative of y, which is y prime. Okay, so here it's three functions. I have e, I have cos, and then I have y. So that's why I put this y prime over there. And then I add the derivative of x, which is 1, and then cos of y will stay as it is. Then I collect all the terms with y prime on one side, so I should have y prime Okay, so the terms with y prime, it's this one here, e to the power of sine x and this one over here. So this is negative x e to the power of cos y sine y, but it's negative on this side. So when I bring it to this side of the equal to sign, it'll become positive. So I have positive x sine y e to the power of cos y. Okay, then I close my bracket. Then on the other side of the equal to sign, this term here did not have a y prime, so I have to take it to this side with e to the power of cos y. Okay, so on the other side I have e to the power of cos y. And we said this one over here, so when it goes to the other side, it becomes negative. Y cos x e to the power of sine x. Okay. Okay, like that. And then I will divide by this term on both sides. So what I have is y prime. This is equal to e cos y minus y cos x sine cos x e to the power of sine x. This is divided by e to the power of sine x plus x sine y e to the power of cos y. Okay, so that is how you would solve that one. Okay, do we have any questions on the chain rule implicit differentiation? Okay, if not, let's look at one more. This is number 4 in the same exercise. Here we are told to find dy dx at a specific point. So remember, dy dx is just the slope, it's the gradient. So if you're given the coordinates of the point after you work out y prime, then all you need to do is work out, just substitute your values of x and y into y prime into your equation. So here the first one, it says x cubed y cubed plus 4y. This is equal to 3x squared. Now we are told to find dy dx, which is just y prime at the point 2, 1. Okay, so that's what we have to find. So in other words, we want to work out the slope at that point. So to do that, we differentiate both sides. Now when we differentiate the left-hand side, we have to use the product rule. So first, I will keep x cubed as it is, Then I multiply by the derivative of y cubed. This is 3y squared. And then I multiply this by y prime. And then I add 3x squared and y cubed. So that is the derivative of that one. Then the derivative of 4y, this is just 4y prime, and this is all equal to 6x. So I need to collect the terms with y prime. So there's this one, and there's that one. Let's see if we can simplify it first. So I have 3x cubed y squared y prime plus 4y prime. This is equal to 6x minus 3x squared y cubed. Then you factor out y prime. This is 3x cubed y squared plus 4. This is 6x minus 3x squared y cubed. And then this means that y prime is equal to 6x minus 3x squared y cubed divided by 3x squared y squared plus 4. Now we want the gradient at the point 2, 1. So we want y prime of 2, 1. So I'm going to substitute x with 2 and y with 1. So this is equal to 6 times 2 minus 3 times 2 squared. And this is 1 cubed. 3 times 2 squared. This is just 1 squared plus 4. So this, you work it out on your calculator. Okay, I'm getting 0. Okay, so what that means when your gradient is 0, that means that it is stationary at that point. So it's like a flat line. Now, when the derivative at a point is 0, that means the tangent at that point is a horizontal line. Because remember, the gradient of the tangent is the same as the gradient of that point. So that means if you have a curve like that, if you draw the tangent at that point, it is a horizontal line. Okay, so this could be a maximum point or a minimum point. Like that. Okay, do we have any questions? Are we fine? Okay, if not, then tomorrow we'll yes. Okay, then tomorrow we'll very briefly look at higher order derivatives. This isn't anything new, it's just adding on that you can actually work out the derivative more than once. So if you have y prime, you can also work out y double prime. That just means differentiate y prime. Okay, and you can also differentiate that again and get y triple prime, the fourth derivative, and so on. So sometimes you have functions that maybe the third or fourth derivative is 0, and then you have other functions. For example, if you have y is equal to e to the power of x, when I find the first derivative, this is e to the power of x. When I differentiate this again, this is still e to the power of x. So I can differentiate this continuously. I will always get an answer. Unlike something like this, if y is equal to x to the power of 3, I can work out y prime. This is 3x squared. Y double prime. This is 6x. y triple prime, this is 6, and then the fourth derivative is just 0. So, and then every derivative after that will be 0. And then other functions like sine x, y prime, this is cos x, y double prime, this is minus sine x, y triple prime, this is minus cos x, the fourth derivative, this is sine x, and then you can see there's a pattern. I'm here, sine x, when I differentiate it, I go here, there, there, I'm back here, then it's like a loop. Okay, so you have some functions where the derivative is just constant, like that one there. Then other functions here where the derivative eventually gets to 0, and then some like this where it's a loop. Then you can try this one, y is equal to ln of x. See what the pattern is, if there is one at all. Okay, so that's just on higher orders. Higher orders just mean keep differentiating. Okay, right, so if there's no other questions, then I will see you guys tomorrow, also at 7:30. Have a good day.
Have a good day, Miss.
Thank you.